latest research, the largest exomoon survey to date, and the detection of our second ever Exomoon Candidate. Stay tuned to the end of the video to learn about how we did it and the shocking nature of what we found. Exomoons. Moons of planets beyond our solar system, objects that have continuously eluded astronomers over the years. For me, the search has been personal, comprising a large part of my research, yet stubbornly, they've remained just out of reach. Throughout my career, each and every search has come with a fresh lining of hope, a wistful skip in our stride as we dare to imagine that this time, despite all of the failed searches of the past, this time might be different. This could be the one. But time after time, I've been left with another disappointment, another no detection, another upper limit. And in all of that, I remind myself that this is how science works. It doesn't care about how I feel, what I want to be true, or how many times I've sat on that park bench dreaming of other worlds. It just is. We don't all get to win the lottery. Sometimes successes aren't born out of luck, but just perseverance. Because what always kept me hopeful is that moons simply had to exist. We see them right in our own backyard, and so planets around other stars, exoplanets, must surely have them too. Exomoons have never been a question of if, but when. So what has this perseverance taught us so far? Well, in the many years of looking for moons around exoplanets, we've largely been limited to planets which are on relatively tight separations around their stars, distances much closer than the Earth's orbit around the Sun. Now, that really wasn't by choice, it was just all that we had to work with. You see, we look for exomoons by watching their planets transit in front of their host stars, possibly revealing extra wiggles and perturbations betraying the moon's presence. But the problem is that this transit method is strongly biased towards finding planets that are close to their star rather than far out. That's just geometry. Transits only work if the system we're looking at is fortuitously aligned to our line of sight, and there's a much larger range of angles for this to happen if the planet is close in rather than far out. So years of exomoon hunting, largely using NASA's Kepler telescope, taught us that these close-in planets hardly ever have moons large enough that they'd be detectable. The fact that we didn't detect anything, really, it's no surprise. There are no moons as large as the Earth in our solar system, and the close-in planets, Mercury and Venus, do not have moons, suggesting that their close-in separations prohibit them. Perhaps, on that basis, as I'm sure many others concluded, there's no point in looking for them. But the story of exoplanet discovery is a tale of constant surprise. Our expectations based upon the solar system were defied at each and every turn, and that really drove our hope. Perhaps exomoons might pull off the same trick. In 2018, that hope saw its first reward. Here in the Cool Worlds lab, my student at the time, Alex Tichy, and I reported the first case where we saw compelling evidence for an exomoon, Kepler 1625b-I. Unlike most transiting planets, it resides at about the same distance from its star that Earth is from the Sun. Yet more, it is a Jupiter-sized planet, a relatively rare phenomenon as only 10% of stars have these. So here we had a rare example of a cool giant planet, and around it we saw two pieces of evidence for a surprisingly large exomoon. The first evidence was a timing offset. The transits didn't occur every orbital period as expected, but instead showed deviations of about 20 minutes, sometimes occurring earlier and sometimes later than expected. This effect, which is known as TTVs, is known to be a consequence of an exomoon caused by its gravitational tug on the planet. On its own, this isn't really enough to get too excited, as other planets in the system could also cause this TTV effect. But what pushed Kepler 1625b-I over the edge was the existence of a second, clear dip in starlight, consistent with a moon passing in front of the star. For the last few years, this has essentially been the only good exomoon candidate that we know about, but it remains a bizarre detection. It's a Neptune-sized moon orbiting a super Jupiter. Neptune and Supiter, as friend of the channel Emily Sanford used to joke to me. And accordingly, for two big reasons, we and many others in the community remained skeptical about the reality of that signal. First, we only really had one good transit of the moon in hand, but with a single blip. How do we know that the star or the telescope didn't somehow fool us? The unknown unknowns loomed large over our detection. This was compounded by the fact that the data didn't even come from Kepler, it came from the Hubble Space Telescope. In particular, we use an infrared instrument on Hubble called Wide Field Camera 3 that is both finicky to work with and has far less data for this star than Kepler, just 40 hours, making the data calibration particularly challenging. And the second doubt was, of course, the nature of the moon itself. No one really predicted such large moons could exist. Now, after the detection, many theorists devised ways to explain its existence. For example, Brad Hansen at UCLA suggested it was originally another planet that got pulled into orbit whilst this super Jupiter was forming. That was a relief, but of course it doesn't prove that our exomoon signal was real. On reflection, I've often compared this weird object to the discovery of hot Jupiter exoplanets. Nobody expected Jupiter-like planets to end up so close to their star, but in the early years of exoplanet hunting, they kept popping up all over the place. In fact, many initially doubted they were even real, thinking perhaps it was just the stars misbehaving in some way that tricked us. But after about a dozen were found, well, there were few doubters left. It turns out that hot Jupiters are in fact remarkably rare. Only 1 in 200 stars have them, but their enormous size and close proximity makes them far easier to detect, and so many were found despite their intrinsic rarity. Perhaps Neptune-sized moons are the same then. They're not very common, but it makes perfect sense that they'd be the first ones we detect because, after all, they're simply far easier to see. But the comparison isn't really fair, because we know of many hot Jupiters, but just one exomoon candidate. Doubts will inevitably and quite fairly remain about the reality of such big moons until many of them can be found. The field of exomoons finds itself with dozens of no's and just one maybe. But in all of that effort, all of the countless hours that have been poured into this search, there is something that we can learn, that planets on close-in orbits around their stars rarely have large moons. Okay, fine, but what about the planets which are further away from their star? What about those? Well, truthfully, we've hardly looked, but in one of the few cases where we did, lo and behold, we see evidence for a large moon. Surely, from this then, we can salvage some hope. We can see a clear and manifest task that emerges from the years of disappointment. That if exomoons exist, then it is around the widely separated Jupiter-sized planets where they will be found. When it comes to exomoons, it is the cool giants that we must survey. In March 2018, what seems like a lifetime ago now, I began the Cool Giants Exomoon Survey, an effort to finally tackle these auspicious worlds. For the last 4 years, I very much wanted to tell you about this work, a project of passion, challenge, and joy. But I felt it was important that we got this right, that we dotted all the I's, crossed the T's, double, triple, quadruple checked all the calculations that went into this, because I think I owe you that. And from all of that effort emerges something that is exciting and tantalizing, a new exomoon candidate. Before we talk about our new friend, and we will, trust me, let's get a sense as to what we did in this new paper, which is linked down below in the description. We started by scouring the exoplanet catalog and published literature to create a list of cool giants, specifically transiting cool giants that the Kepler mission detected. Kepler is really the only game in town for this. No other transit survey stared so patiently at the sky, enabling the discovery of these long-period worlds. I made the decision that cool giants would be defined as candidate planets that satisfied 3 basic criteria. 1. They had to have orbits wider than that of the Earth. 2. They had to be at least half the size of Jupiter. And 3, they need to have at least 2 recorded transits by Kepler. The first criterion is a little hazy as stated because the mass of the host star is going to affect the planetary orbits. So to combat this, we include anything that has a period greater than 400 days, or it has an effective temperature cooler than that of the Earth. This left us with 73 exoplanetary candidates, although in the end we had to throw out 3 of those for having unacceptably poor data quality, thus leaving us with 70 cool giants. The next step is going through the light curves of each object, so that means that we're looking at how the brightness of each star changes during the Kepler mission. When the planets pass in front of the star, we get a nice big dip. That's the transit. But the light curves show all sorts of extra wiggles due to slight changes within the telescope itself, as well as the intrinsic variability of the stars themselves, something we have discussed at length in one of our recent videos. Here in the Cool Worlds Lab, we have developed a state-of-the-art approach for correcting these effects, known as method marginalized detrending. Many teams have come up with different algorithms for correcting these effects, each with their own different pros and cons. Now, rather than us arguing about whose algorithm is best, what we do is just use all of them and let them vote on what the right answer is. Here I'm showing you an example, and as an extra cherry on top, we use the level of disagreement between the methods to adjust the measurement uncertainties appropriately. By using so many different methods, this is of course a time-consuming process, but it ensures that we get light curves that we can really trust, not subject to any particular method's often arbitrary assumptions. Next, we go through each of these corrected light curves and fit different physical models to the dataset. In particular, we ask how well does a planet by itself explain the data versus a planet with a moon. And in order for an object to be considered an exomoon candidate, we demand that the planet with a moon model is at least 10 times more likely to explain the data than the planet by itself model. That's known as the Bayes factor. This 10x threshold might seem arbitrary at first, but it represents the canonical standard of strong evidence in model selection studies. As a final check, we demand that our fits favor a circular orbit for the planet because highly eccentric orbits are thought to be unstable locations for exomoons. The product of our extensive search is that 3 planetary candidates formally pass all of our tests, with these not so catchy names shown here. So does that mean that we just detected 3 new exomoon candidates? Well, here's where the hard work truly begins, because correcting and fitting transits is certainly challenging, don't get me wrong, but truly understanding what you are looking at, that is another level entirely. Let's go through each of the 3, starting with what I'll call KIC 868 for short. KIC 868 has just 2 recorded transits, and looking at them, one can see how 2 features are driving the exomoon fit. First, the transits have very different depths. The moon fit tries to explain this by thinking that the first transit is the planet and moon transiting together, causing a deeper transit, and the second transit is just the planet by itself, thereby requiring the moon orbit to be oriented in such a way that it doesn't transit every time. The second piece of evidence is an upward spike occurring inside the first transit, as you can see here. Now, that could be caused by a moon passing in front of the planet during the planetary transit across the face of the star, something known as a syzygy event. Now, both of these evidences could be pointing towards an exomoon, but they also have much more mundane explanations as well. The spike could instead simply be the planet eclipsing a star spot on the stellar surface, something that we often see in Kepler data. And the depth change? Well, the telescope actually rolls over every 3 months, as I'm showing you here, and that causes stars to land on slightly different pixels each quarter. As a result, it's possible there's a hidden star nearby that dilutes the transits in one of these quarters more than the other, hence causing a depth change. And trying such a model actually yields a better fit to the data, no moon required. However, I have to say I have some mixed feelings about rejecting this moon candidate because both of these alternative explanations I've offered you aren't really satisfying either. We can tell that the star spot activity appears generally quiet over the 4 years of data in hand, varying by less than 200 parts per million, but in contrast, the spike that we see is about twice that amplitude. And although a hidden star could explain the changing depths, there is no such known star, and high-resolution Gaia imaging puts quite tight constraints on this. So maybe this is an object that's worth keeping an eye on in the future, but in this study we really err on the side of conservatism and use any excuse we can to kill Exomoon candidates. On that basis, KIC 868 is rejected. Next up, the second promising signal is Kepler 150f, a previously confirmed sub-Jupiter planet on a 1.7-year period. Again, there's only 2 transits to work with here, but the most striking thing about this guy's light curve is the high variability. Remember how KIC 868 varied by 200 parts per million? Well, this one varies by 50 times more, reaching 1% levels. That's generally what we'd consider to define an active star. So that means that the star is littered with star spots across its surface. So the immediate concern here is that these spots might trick us, might fool us into thinking that we're looking at an exomoon because they cause these modulations inside the transit shape. Indeed, in our paper, we found that a model with 2 spots is able to convincingly outperform either the planet or the planet plus moon model and is fully consistent with the high variability that's seen. This again is enough to cast some pretty serious doubt on the exomoon hypothesis, and so it was summarily rejected. And so this leaves us with just one remaining candidate, KIC 790, one last glimmer of hope. At this point, I was certain that it would end up on the scrap heap along with its predecessors. After all, that's been the story of not just this survey, but the years of searching that I've personally devoted to exomoons. I've almost been conditioned to be skeptical of everything I see after so many letdowns, and I'm sure many of you can relate to that feeling. And so I admit, I went into this one almost prejudging it, assuming it wasn't real, because after all, it's mentally safer to do that than to continuously hold out hope after so many failures. Nevertheless, let's see what the data reveals. The moon fit shows a satellite that transits a little bit ahead of the planet in the first transit, causing this pre-transit shoulder feature. If that's really a moon, then it should cause a counter shoulder about 1 transit duration later inside the planetary transit as the moon exits, and indeed that's what we see. The second transit shows hints of the same effect, but not so clearly. Whilst the signal is tricky to see by eye, the Bayes factor tells us that the moon fit is 11.8 times more likely than the planet model, a 4.8 sigma signal. Okay, fine, this is probably just a star spot again, right? Well, no. Star spot crossings can only happen inside the planetary transit. They can't happen before the planet even enters the stellar disk because, well, there's nothing to occult the spot. Okay, fine, maybe it's landing on different pixels again, just like KIC 868 did, causing some weird effect. Well, no, this time the transits are separated by exactly 8 quarters, so 2 full revolutions, meaning that the star lands on exactly the same pixels as before. Okay, well, surely it's an artifact of our data correction then. Again, no. Looking at the 8 different detrendings that we tried, the same feature persists every time, and the moon fit is better in every case. Alright, fine, you want me to get creative? You want me to come up with some way to kill this stubborn hope? Fine, I can do that because guess what, my friend? I've been doing this a long time. This is not my first rodeo. And I remember how 8 years ago I killed another Exomoon candidate by developing a novel pixel level analysis. Let's bring out the big guns. Okay, here's the actual image of Kick 790 that Kepler took. It's not so impressive, just a 5x4 pixel grid with the star located inside that box. Usually we add up those 4 inner pixels to make the light curve, but we could instead use each pixel individually to make separate light curves like this. From each pixel light curve, we can now measure the transit signal to noise ratio that we find. As totally expected, the peak occurs where the star lives. Nothing surprising there. That makes perfect sense. Okay, now let's do the same, but for the exomoon signal. Again, it lives on top of the star as expected, but critically, it was this test that another exomoon candidate failed 8 years ago. For Kepler 90G, the moon signal's noise was regurgitated all over this pixel grid, a symptom of the electronic detectors misbehaving rather than a real exomoon. Curiously though, Kick 790 once again passes this test. At this point, I was getting pretty frustrated with this object. Why wouldn't it just lay down and die like the rest of them? Why was it still insisting on pretending that it was an exomoon? Just give up already. I'm gonna break you eventually. It was at this point that I called in colleagues from the Kepler mission and asked them to take a look. After all, the planet in question was still just a candidate planet, not a confirmed one. Perhaps they would be able to find some evidence that it was in fact a false positive. When colleagues Steve Bryson and Jesse Christensen emailed me a few weeks later that their analysis found that it was almost certainly a real planet, another possible avenue was closed off. Yet more, Kick 790 had now been upgraded in name to Kepler 1708b as a bona fide exoplanet. This really wasn't going in the right direction at all. Next, I worked with another Kepler veteran, Chris Burke, to consider maybe this extra transit signal is real, but it's not a moon, just another planet that happens to transit at the same moment in time. Once again though, the moon apparently survived this test, with the hidden planet hypothesis having dismal odds of working out. More and more tests we tried. For example, inspecting the noise properties of the light curve around the transits to see if there's any kind of irregular behavior. We also tried looking at the timing of the moon transits themselves to see if they were somehow suspiciously unlikely. But Kepler 1708 just kept coming back for more. The final test that I could think of, and one that came with huge computational cost, was to inject a planet-only signal back into the original data but at random times, and then count up how often would we erroneously claim an exomoon. This is known as injection recovery. We inject a known truth, in this case a planet by itself, and push it through the entire pipeline discussed so far, and then ask how often would we erroneously conclude that there was an exomoon. The resulting number is known as the false positive probability, FPP. Think of it as the probability that we're wrong. After 200 injections, this analysis determined that the false positive probability was 1%. In 1 out of 100 cases, the random noise properties of the star itself would conspire in just the right way to trick us into thinking that we were looking at an exomoon. In many ways, this percentage is actually really frustrating though, because it sits right at the threshold of when we would start to call something a discovery. Conventionally, a planetary candidate is promoted to a real planet if the false positive probability is 1% or smaller. I wish this number were either 0% or in the tens of percent, sort of definitively settling the issue one way or the other. But then again, that would be just too easy, wouldn't it? This is exomoons after all. In the end, as preconditioned as I was from years of negatives to believe that this thing would surely be just another illusion, no matter what I did, how many tests I threw at this damn thing, how hard I tried, and I really tried, I can't kill it. It won't go away. Kepler 1708b-I is That stubborn residual stained on the bottom of the pan, scrubbed until your hands bleed, but it's still there, still staring right back at you. So here, at the end of the video, I'm going to finally tell you about the properties of this moon candidate, because only now have we got to a point where I think that the moon parameters are actually worth mentioning. Kepler 1708b is a validated 0.9 Jupiter radius planet on a Mars-like 737-day orbital period around its solar-type star, one which is 5,700 light-years away from the Earth. The moon candidate is 2.6 times larger than the Earth and lies about 12 planetary radii from its planet. That's about the same distance as Europa orbits around Jupiter. The moon mass is unknown, but it's constrained to be less than 37 Earth masses, and given its radius, it's what we would call a mini Neptune. The orbit of the moon candidate appears consistent with a flat, coplanar orbit with a period of order of several days. We don't know how massive the planet is. It could be anything from Saturn mass to tens of Jupiter mass given its size. The larger end of that possible range would potentially indicate that the moon formed in a similar manner to Jupiter's moons, forming from the disk of leftover material around the planet. If it's on the lower mass end, we'd likely need to invoke some kind of capture scenario to explain it. In our paper, which has been published in Nature Astronomy, we urge that this object should be considered an exomoon candidate, and further observations are necessary to either confirm or reject its reality. But if they are real, Kepler 1708b-I and 1625b-I seem to form a new class of astronomical objects, Neptune-sized moons around cool giants. Whilst the existence of such large moons was not anticipated, if they're real, they would of course be the easiest sized moons to detect and thus would naturally represent the first ones we'd find. But on the other hand, they both live just above the boundary of detectability, where perhaps we are just being fooled by the data in a way that we don't yet understand. As for me, well, I've been doing this long enough to learn that it is the data that we have to follow, not my instincts, not my desires, not my priors. And in this case, the data are telling us that there is an exomoon candidate here that we cannot kill, despite our considerable efforts to do so. But of course, that does not in of itself prove that this is real beyond doubt. We have something here that's exciting, enticing, but ultimately we are at the beginning still of a very long journey. We will one day discover many exomoons, of that I'm sure, and we will surely look back at these early steps with a clearer perspective. But for now, we must wait for more data to guide the way and remain patient. This work takes a lot of that, and so I want to personally thank the donors to the Cool Worlds Lab who have enabled this research. It's through your support that we're able to keep this fire alive. Whilst this dream might be bigger than any one of us, it's something we can all make a difference to. And so I want to personally dedicate Kepler 1708b-I to our supporters, the Cool Worlders. Looking ahead, the game is changing. In my team, we've been developing wholly new methods to look for exomoons that look set to shift the sands in our search. It's been a long, cold night looking for exomoons out in the dark, but I feel like a new dawn is rising, and I can't wait to share the new discoveries that emerge from it with you right here. So until next time, stay thoughtful and stay curious. Thanks for watching, everybody. Just want to say, if you like our stuff, then be sure to click the subscribe button down below. And if you really want to help us out, you can become a donor to our research team, the Cool Worlds Lab, right here at Columbia, just like these awesome people did. You can use the link up above to hit that. So until next time, have a cosmically awesome day out there.